We're going to take a little bit of a deeper dive into Hadoop file system and look again at some of the trade-offs and maybe mention some new ones that we mentioned in previous lesson. As I had mentioned, HDFS is optimized for streaming reads, and that makes it very poor as a random seek file system. And the streaming reads make it very fast for the type of processing that MapReduce does. So it's a trade-off in terms of the actual file system that gives us better performance. I mentioned also that it's a write once file system. Files are written once to the Hadoop file system, and they can be deleted. However, they are not changed. There is some work in the process to allow them to be appended to, and generally the idea, though, is that the first write of the file is the only write of the file, and it doesn't get changed. It can be copied, as we'll see in a little bit. There's plenty of things you can do, but you generally can't write to a file as you could in a normal file system. There also is no local cache needed, and this is largely due to the fact that the files are very large. The block sizes of the files and the files are large, that caching really wouldn't be of much use because we're streaming through a file, not rereading a file. So caching usually plays a pretty big role when you've got multiple access of repeated access into a file. In this case, the streaming read doesn't really benefit a caching system. Next, the idea that hardware can fail was mentioned, and hardware will fail. What will happen is you may see reduced performance, but systems will still run. Actually, the amount of failure that can be tolerated by Hadoop depends largely on some configuration, but it is designed to allow one machine to fail and even possibly a whole rack of machines to fail within a data center. So as many of you know, there's individual machines in a rack, and it's possible that something happens that the whole rack loses power. And it's possible to run Hadoop so that it doesn't cause even a rack failure to knock out your system. Again, you will see some degraded performance, but things will still run. The other trade-off is that it is not a general purpose file system. And it's a specialized file system for Hadoop use and mostly MapReduce use. So the HDFS file system was based on the Google file system that was described in a paper published by Google. And this can be, you can find this on the web. The concepts are very similar. Most people often get a little confused because using the Hadoop file system is not like using your local file system where you can do lots of different processes on any file anywhere. So there's lots of things we can do, and we're going to take a close look at what we can and can't do in a little bit. Next, I want to talk about some of the different nodes and roles that Hadoop plays. I'd like to introduce the concept of the name node and the data node in the Hadoop file system. Now, I want to do a little sidebar here and mention that there's different types of nodes in Hadoop. And these nodes generally are on a physical system, a physical server. And a server may be supplying different services for different nodes. So we're going to talk about data nodes, and they could be, and usually are, very similar to processing nodes that are used for the MapReduce processing. So please don't assume that when we mention a specific node that it's an individual node doing a single service. That said, there's times with large Hadoop systems where we can have a single server act as a node that has a specific job that requires a lot of processing power. So we dedicate a single node to a system. Now, getting back to Hadoop file system, the Hadoop file system works on a master-slave model. And it basically uses a master node called a name node. And the name node is what oftentimes is referred to as a metadata server in file system parlance, or I like to think of it as a data traffic cop. Basically, the way it works is everything that happens goes through the name node. In a second, we'll take a look at that in more detail. But the name node is what's really important. The name node actually provides to the end user a single namespace. So if I'm going to look at the Hadoop file system, I'm going to see one namespace for the whole file system that is, again, spread across a bunch of servers. So it's going to look like a normal file system where I'll have a hierarchical naming system. The data nodes is actually where the data live. So the name node really is more or less like the traffic cop, telling us where to find or write data. And these goes to the data nodes. The name node also handles failure of data nodes. And this is where we start to get some idea of some of the redundancy and fault tolerance built into Hadoop. The data node might fail, and if it doesn't report in a certain amount of time to the name node marks it as down and begins to work around it. So it basically takes it out of the process. And because it's a traffic cop, a central traffic cop, it can do that. To better understand this, I'm going to bring up a diagram here that shows some of the roles and some of the nodes in a typical Hadoop installation. So we're going to start with the client node, which is where the end user may be using Hadoop. And we're also going to have a name node, which could be on the client node or could not be. It could be a separate node. And then we're going to have data nodes, and then we'll have something called a secondary name node that we'll get to in a minute. So the HDFS data live on the data nodes, as I had said. So we have 3 data nodes in this depiction, and that constitutes our distributed file system. Again, files that we write to the file system get striped across these data nodes. As a user, when I want to access this data, either writing it or reading it, first thing I have to do is ask the name node, where do I read or write data? And then the name node will come back and say, use these nodes. And then you can see there's a series of arrows here pointing from the client to the data node. So now the client knows where to find the data. Now the parallel piece of this is, if I need to read data, I'm reading it from 3 different nodes or 2 of the nodes, depends which data node it's on. And the data comes back to the client looking like a single file system. Same with writes. We can write to the data nodes, and the name node determines where things get written to the data nodes. And then when we look at the file, it looks like a normal file system with files in it. So again, the name node is the traffic cop. It tells us what and where things go. The name node also monitors the status of the data nodes. So the process really is designed to let the client work with the nodes in parallel and allow the name node to manage all the details. And again, when the client writes, the name node manages all the information as to where things are going to go and what node they go on, etc. And we'll take a closer look at that in a minute. The point is, from the client standpoint, they don't have to worry about it. Everything goes through the name node, and it manages everything, including, as I mentioned, failure of the data nodes. Now there's another box on the bottom here called the secondary name node. And it's also now called the checkpoint or backup node. A lot of people assume the secondary name node is a failover node for the name node, and that's not true. The secondary name node, really what it does is checkpoint the name node file system so that in the event that the name node goes down, it can be restarted using the secondary name node image snapshot, which is very much different than a failover where if the name node failed, it would flip over to the secondary name node. That's not how it works. So it's possible in some small clusters that the secondary name node may actually even exist on the same server that the name node is running. Or it could be running on a separate server, or it could be running on one of the data nodes. So again, getting back to this idea of where certain services run is not necessarily determined by the physical hardware, but more on terms of the functionality and how much of a load the service needs. Indeed, there are some systems where, for demonstration purposes, all these services would be running on a single node. The file system namespace is actually very similar to what we're used to dealing with in almost any file system. It supports files and directories, and HDFS also supports many of the commands that we're used to using in a Unix or Linux file system. And these include create, remove, move, rename, copy, etc. The important thing to remember is these operations happen through the name node. We actually have a little bit of a wrapper, and we'll show this in the examples, a wrapper that goes in front of these commands that tells it to operate on the entire Hadoop file system. It's important to note that if we look at the data on the data nodes without going through the name node, we don't see the files as we would expect them to see them in our Hadoop file system. And that basically means we're going to see things we don't understand. And I'll have an example of that later on. So the way to manage the Hadoop file system is through the name node and not on the individual nodes themselves. Although the data certainly is there to be looked at if you want to. Indeed, really what it does, it just uses the underlying file system on the data nodes to store blocks of data in a Hadoop or HDFS directory of some sort that we'll set up. We'll take a look at that in a little bit as well. There are some limitations that HDFS does not yet implement user quotas or access permissions. Since if you think about it, the file is write only, write once, so having a write permission doesn't make sense if you're not allowed to write to a file after it's created. There's some other permissions that don't map well into HDFS. And also HDFS doesn't support hard or soft links. And it should be mentioned that HDFS architecture doesn't preclude implementing these features. It's just that many times in the type of processing we do with MapReduce and Hadoop, there's no need for these type of features at this point for many of the operations. Hadoop file system offers redundancy through data block replication. And that can be understood very clearly with this diagram on the current slide. First thing to mention is that in Hadoop file system, data blocks are 64 megabytes in size, which is much, much larger than you typically find in most file systems. A typical file system may use a 4 or 8K data block size, and Hadoop is over 100 times bigger. The reason for this, because it is a streaming file system in a sense, we get better performance over big data blocks. And since we're using big data, the smaller the number of the blocks that we would use, the more overhead it would require for the file system to manage all those small blocks. Again, one of the trade-offs over a traditional file system, however, this is designed to speed MapReduce processing. So what happens when we write data to a file? So let's assume that we have a file that is 5 times 64 megabyte blocks, and it's okay if the file is a little shorter or a little longer. It'll take care of that. So what happens is when we write that file to a Hadoop file system, and let's assume that our file system here now has 8 nodes, and from our client node we're going to write this file into Hadoop file system. What happens behind the scenes is HDFS breaks this up into 5 parts, 5 64 meg blocks. And then what it will do is it will take the first block and put it on a data node. And then it'll take another block, the same block, and put it on another data node. And then it'll take the same block again and put it on yet a third data node. Now, this level of replication is tunable, and it can be set in the configuration file. So you can set it to 1 where you have no replication, which isn't generally a good idea, or you can set it to higher, like 4 or 5 if you think more redundancy is important. Generally, the default is set to 3. So if we take every block of this file and break it up into 5 blocks and we sprinkle them, and what the HDFS will do is, the name node in particular, we'll sprinkle these throughout the nodes and making sure that if any one of these nodes goes down, we don't lose the data. So for instance, if it sprinkles the nodes in this fashion, and this node down here, the node with 1 and 4 on it, blocks 1 and 4 goes down, it also knows the name node, again, because it's the traffic cop, it knows another node copy lives on another node of each of these blocks. And what's important is the way it sprinkles these blocks is it can handle actually multiple outages with large numbers of nodes and still maintain copies of the data. So the important feature here is redundancy comes through replication, and the replication is done by the name node to a certain level of replication, and it allows us to implement a system where if things fail, the data still exists somewhere in our HDFS. I'd like to take a closer look at the process used when a client reads from HDFS. This may be important to understand a little bit about what actually happens when data is read from HDFS. We'll take a look in a second about writing data to HDFS as well. The first step that happens, as you would guess, is there is a call. The HDFS client works through the instance of distributed file system. And the distributed file system calls up the name node, the traffic cop, and returns the data nodes that have a copy of that block that we're interested in reading. So we've essentially told the name node, here's the file we want. And the name node returns us the data nodes that have copies of those blocks of the file. Then what happens is the data nodes are sorted according to their proximity to the client, according to the topology of the cluster, and we'll talk a little bit about that later. So if a client node, and there may be multiple client nodes, is closer to the data as stored in our, as we mentioned before, on different nodes, different blocks, it'll try and locate the closest block to pull from. Sometimes, in terms of our MapReduce task, the client node is the actual data node, and that's where we want to perform the computation. So the point is that the name node is definitely aware of where data lives in the Hadoop file system. The next step is that the distributed file system returns a file system data input stream to the client from which it will read and write. So the client will actually go through this file system data input stream to read and write, and that the file system data input stream manages the I/O and the communication with the name node. So as we can see there in step 3, the connection is made to the file system data input stream, and at that point, data is streamed from the data node back to the client. Again, we're doing this using information from the name node and proximity and so forth, so the data begins to come in and repeatedly over that input stream, and when one end of a block is reached, it will open a connection to the next best data node, so forth and so on. Now you may wonder, like, why does it wait till the data is delivered until it moves to the next data node for the next block? And that could very well be because for some reason, possibly the system went down, one of the data nodes went down, and the data node you needed for your read isn't there anymore. So the name node, again, is aware of what's working, what isn't. So if the node isn't there, it'll flip you to another node. It'll be able to provide another node to find the data because we've replicated it across systems. So when this is all done, there'll be a step 4. In this case, there's 3 read steps, and again, not every node has every data block in it, so there's some data nodes that won't contain data, and certainly in a big system, that's certainly possible. Again, it's transparent to the client, which is just like reading a file stream from a file system. In step 5, once the data is complete, it does a close call on the file system data input stream, and the file's been read. So it's pretty much from the user standpoint, there's an open and a close in the client program. Everything else is managed through the system. Next, I'd like to take a look at client writing to the Hadoop file system. You'll notice the diagram is somewhat similar to the read, only writing is a little bit more trickier, and we'll see how that pans out in using this diagram. So again, we'll start out by calling a create, and of course we go to a distributed file system wrapper, which makes the RPC call to the name node to create a new file. And again, the name node is the one that determines where the data is going to go. There's also at this step, if there's any permissions that need to be taken care of, the name node takes care of it. And again, without writing any data to the data nodes at this point, because it holds the metadata, it knows what permissions are supported and what's available, and it will return, if there's a permission problem, it will return that information. So just as in the read case, then if everything checks out, there's a file system data output stream process that wraps an output stream that the client talks to. At this point, the file system data output stream handles the communication with data nodes and the name node. The client doesn't get involved in the process any further. As the client writes data, which is step 3, the output stream splits the data into packets, which it writes to an internal queue called the data queue. The data queue is consumed by the data streamer, whose responsibility it is to ask the name node to allocate new blocks by picking a list of suitable data nodes to store replicas. And again, remember, we're going to replicate data when we write to the Hadoop file system. When it gets back its list of data nodes, it forms a pipeline. And in this case, we'll assume that replication is level 3, so there are 3 nodes in the pipeline. So we're writing a block of data to 3 nodes because we're replicating 3 times, performing a pipeline for the replication. The data streamer streams the packets to the first data node in the pipeline, which stores the packet and forwards it to the second data node in the pipeline, and then on to the third. And that you can see in the diagram where I have a 3-stage pipeline, and the data is transferred between nodes, which is step 4. Once the data has been written, there's an acknowledge step, which is step 5, that says, yes, everybody's got the data that has been written to the data nodes. Now, it's also important to know that it will not get this acknowledged until it's sure the data has been replicated on all 3 nodes, the number of nodes we determined to use for replication. It's also possible that data node could fail while data is being written to it in this process. And again, the failure gets communicated to the name node, and it can reinitiate the task and rewrite the data to other nodes. Finally, in step 6, from the user perspective, the remaining data is written to the file system data output stream, and the write is closed, and all the remaining data packets are flushed to the data nodes. And again, there's a wait until there's an acknowledgement that before all the data has been written, before the name node is signaled, which is our last and final step, step 7, that things have been complete. So then the name node can basically rest assured that where it's told to write the data, that it's been written and the data is there and everything is in good shape. So the process here, again, is how data gets to and from, in this case, writing to the Hadoop file system, and to show you that it's not as simple as just writing to a disk drive, that there's a lot of steps that it goes through, and that there's a lot of consideration for redundancy.